Hey everybody, this is Mr. Ainsworth, and we're going to get into section 5 here in chapter 5 and talk about what are called the Euler's theorems, okay, from the famous mathematician back in the 18th century named Leonard Euler, who was the inventor of graph theory, by the way. What we want to do is investigate whether it is possible to determine whether a graph has an Euler path or an Euler circuit without necessarily having to find one explicitly, which means, you don't have to do the tracing, okay? Wouldn't it be nice to know where to start and where to end? Wouldn't it be nice to know that even before you begin testing it? And guess what? There is a way to determine that. So our first investigation here, we're going to take 5 simple graphs and we're going to take a look at whether it has a circuit, Euler circuit or Euler path, and starting at any vertex. And we're going to investigate the degrees of the vertex, the sum of the degrees, and the total number of edges. We're going to do this investigation to determine what Euler came up with a long, long time ago. Before we do that, though, let me just remind you of something here. We're going to go back to previous section here, and I want to talk about and review what we came up with. If I can get it going here, there we go. What it means to be an Euler path and Euler circuit. So take a look at what we talked about in the previous section here. An Euler path is a path that travels through each edge only once, okay, where the start does not equal the end. So on an Euler path, you hit every edge exactly once, so you can't retrace an edge. But in this case, the start does not equal the end point, as indicated up here in our practice, okay? Like in the first graph, we started up here in the upper right, and we ended in the lower right. And because that was an Euler path, an open Euler path, okay, where the start does not equal end. In a circuit, an Euler circuit, we hit every edge exactly once and we start where we end, or we end where we start, okay? So an Euler circuit is a circuit that travels through every edge once, where the start equals the end. So today we want to figure out, through some investigations here, some of the Euler theorems that he came up with a long time ago. And we do that by investigation versus just, stating the actual theorem, okay? So we're going to take these simple graphs up here, and we're going to start at a vertex, and we're going to see if it has a circuit or path first. So let's take a look. Sorry about that. Let's take a look at the graph one at a time and see if we have a circuit or a path. All right, so here we go. Let's say that we start at point B. Let's just say that, okay? So I'm going to write down start here. All right, and I'm going to cruise around. I'm going to hit every edge once. So this is my step 1, 2, 3. So from B to A to D to C. All right, back to B again. So I have 4 edges up there, and I traveled each edge exactly once. And notice that my start point equals my end point. Okay, so in this case, we have a circuit. Okay, sorry about the interruption there. So we have a circuit in this case because we started at B and ended at B. That was B to A to D to C back to B again, okay? And notice that we started B and ended B. So we have a circuit there. I'm going to switch to red. I always do my notes in colors here, 2 colors. We're going to put the degrees in red. And the degree of A, there's 2 edges going in A, so the degree of A is 2, and for D is 2, and this is 2, and this is 2. So 2, 2, 2, and 2, they're all 2, and notice that they're all even, okay? That's something that Euler noticed when he was studying the graphs here. Okay, all even degrees in red. Maybe there's a connection there. Maybe that happens all the time with a circuit. I don't know. We're going to find out. You do this by investigation, and then through the investigation, you come up with the major ideas. These, by example, are not a proof, but they kind of give you an understanding of what he came up with and also the legitimacy of what he came up with. All right, on this one here, on the second graph, I'm just going to pick a starting point. I'm going to pick up here. There's a reason for that, okay? And I'll talk about that as we go through here. We're going to start at A, and let's suppose I cruise down here to C first, all right, and then I cruise over to D. I could do that, or then I can go up back to A, and then across to B, so step 3, step 4, and then down here, step 5 would be back to C, or not back to C, to C, so this is my ending point. So notice that I started at A and ended at C, okay? And that's what's called a path, not a circuit. So I went from A to C to D, back to A, to B, to C. So notice that my start point was A, and my end point was at C. And that is an Euler path. We hit every edge exactly once. Okay, we went through the same vertex more than once, but that's allowed. We only hit or traveled each edge exactly once, and that's important. That's part of the definition of an Euler path and circuit. Each edge exactly once. All right, and what are the degrees? Well, let's put those in red. So the degree of A is 3, B is 2, C is 3. That's another odd number, and then D is 2. So A is 3, and then B is 2, C is 3, and D is 2. So notice here that we started here. We started at A. We ended at C here, and notice that we ended at the odds. Take a look at that. Okay, we use the odd vertices for the start and end. Okay, maybe that happens every time. I don't know. Let's figure that out. Okay, by investigating some more here. Oh, let me back up. I forgot the sum of the degrees. Okay, so back here. So sum of the degrees here. So let me see. 4 times 2 is 8. All right, and then right here, let me put this in black here. 8, and the total number of edges, we only had 4. Maybe there's a relationship between the sum of the degrees and the number of edges. So right here, is there a relationship between the two? Let me write that down. So is there a relationship, all right, between the two? Between the two, question mark. All right, between the sum of the degrees and the total number of edges. You can't really see that after one example. So what we have to do is we have to do it 5 times in a row at minimum to actually see that. Here we got 3 and 3 is 6, plus 4 more is 10, so 10 total degrees right here. And the number of edges, well, there's 5. We already counted them. Step 1, step 2, 3, 4, 5. There's 5 edges. So we look here, 10 versus 5, or 5 versus 10, 4 versus 8. Maybe there's a relationship there. Okay, maybe there's, if you know the degrees, you can figure out the total number of edges and vice versa. I don't know. Let's keep on working here. Okay, so on the third one, we got the third graph here. Let's suppose that I start here. Okay, so let me start. And you just got to pick a direction. So let's suppose I cruise down here. This is my step 1. Right here, you got to go this way. Step 2. All right, step 3 this way. Back up here, 4. All right, and then this way, 5, and then back this way, 6. I ended back at A. So I have 6 edges there. 6 edges. What's the sum of the degrees? I don't know. Let's figure out the degrees. So we got 1, 2, 3, 4 up here. So this is 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, 4 right here, and then 2 right here, and then 2 right here. So 4, 2, and 2. So A and B are 4. All right, C and D are 2. All right, 6 and 6 is 12. So we have 12 total degrees. You know what? Let me put the degrees in red here. So the total degrees here are 6 fourths. That's 10. And then right here, this is 8. And then I'm going to put the number of edges in blue. That's what I'm going to do because it's color code them, right? Oops, that's wrong. 5 edges right here. All right, and then right here, this should be 4 edges. All right, so the edges are in blue, and the degrees and the sum of the degrees is in red. It kind of corresponds with it. And notice here, 4, 4, 2, and 2. Guess what? They're all even again. And let's put that in red. All even. Let me see. We had a circuit here because we start and end at the same place. We have a circuit, and they're all even again. Here, the first time, we had a circuit, and they're all even again. We have 2 cases now where they're all even, and we have a circuit, which means we start and end at the same place. Maybe there's a connection there. All right, let's investigate further. So in graph 4, all right, let's suppose I start right here. All right, I'm going to go step 1, step 2, step 3, step 4. All right, so there's 4 total edges. And that's, let me see, I ended right here. Okay, I start in a different spot, so that's a path. That's an Euler path because I crossed every edge once, or I traveled each edge once, and my start point does not equal end point. I went from A to B to D to C to B. On the previous one, that didn't happen, so I went from A to D, right, to B to C to A to B back to A. Okay, so now let's look at the degrees here. Up here at the top, that's degree 1 at A. At B, 1, 2, 3. At C, 1, 2. And at D, 1, 2. So here, 2 and 2. So notice right here, I got two odds. And my start point was at A. And my end point right here was at B. I started at an odd and I ended at the odd. Over here in graph 2, I started at an odd and I ended at the odd. Exactly two odds. So exactly two odds. Over here, exactly two odds. And in both cases, I have a path. When they're all even, I had circuits. Maybe there's a connection there. I don't know. Keep thinking. All right, graph 5. So let's say that let's say I start right here. Okay, at point A here, or excuse me, point F. Okay, so let's say I start at point F, and I just cruise along the graph. Step 1, step 2, step 3, 4, 5, 6, and then 7. Here, I ended at point C. So I traveled each edge once. I started at F and I ended at point C. So let me write down my path. So F, C, D, E, F, A, B, and then at C. So I started at F and ended at C, which means I have a path here. All right, let's take a look. And then I had a total of 7 edges. All right, so let's take a look at the degrees. Degree 2, degree 2, degree 3, degree 2, degree 2, degree 3. And look at the 2 degree 3 vertices. I started at F, degree 3. I ended at C, degree 3, and everything else was 2. So 2, 2, 2, 2. So notice this one here, exactly two odds again, exactly. All right, two odd vertices. Again, and we had a path. So there's got to be a connection there. And the sum of the degrees, if we add these up, let me see, we have 6 and 8, 14. So we had 14 here. Here we have 5 and 3 is 8. So is there a connection between the sum of the degrees and the edges? Is there a connection between the fact that we had exactly two odd vertices in a path every single time? Is there a connection between the fact that we had even vertices, all even vertices, and the fact that we had circuits in all those cases? Okay, in case 1 and in case 3. Is there a connection there? And the answer is obviously yes. And this is what Euler figured out back in the 18th century when he was alive between 1707 and 1783, was that there is a connection, and he went on to prove it. So he formed graph theory. He was the inventor of graph theory, and he actually came up with the initial set of ideas, which we're going to start writing down right now. Okay, so what do you notice about Euler circuits and Euler paths? Well, I kind of just went over it, but let's be specific here and let's write it down. Okay, what type of vertex can you start and end with? Okay, so if you let's see. For Euler's, okay, we got to separate this. Let's talk about circuits first, and then we're going to talk about paths next. Okay, so Euler circuits. So let me go back up to the graphs on circuits. So that's right here. We got two circuits. So let me put this in red here too. We have a circuit here, and we have a circuit. So look at graphs 1 and 3. Okay, first of all, I just picked my starting points at those arbitrary locations. It turns out you can start anywhere, okay? So the very first thing I'm going to state here is that I can start and end, okay? Start, end, anywhere in the graph. I didn't have to do it where I chose. I could have done it anywhere. Okay, so you can start and end anywhere. Okay, first of all. Second of all, you're going to start and end at the same vertex. So wherever you start, okay, you're going to end there. So start and end, okay, at the same vertex. At the same vertex. Okay, so you can start anywhere you want, and wherever you start, you're going to end there. So the second point here is the important one. You're going to start and end at the same vertex. And what do all the vertices have in common? Well, let's go back up to the top. If you look at graphs 1 and 3, all right, all the vertices in graphs 1 and 3, they're all even. Okay, for the two circuit cases, I ended up with all even vertices. That's what they have in common. So when you notice that, you know you have a circuit. Okay, so all vertices are even. So remember that. And the simple case is right up here. There we go. All right, graphs 1 and 3. Okay, now in the past that wasn't the case. Now in Euler Paths, okay, again, I'm separating these two things. Euler Paths always start and end at the odd vertices. I'm going to go back up top and show you. Now, I knew that before I did this, and you didn't, but I did, because I'm one step ahead of you guys. But I saw the odd vertex at A, and C, so I knew I can start at either A and C. If I start at A, then I end at C, and vice versa. That's for graph number 2. Graph number 4, I could have started at either B or A. I started one and end at the other. So you need to identify where your odd vertices are first, and always start and end at an odd vertex. So always start, okay, or end at an odd, well, start and end at an odd, whoops, let me spell that better, at an odd, underline odd vertex. It's important. You can't do it any other way. Okay, it just flat out won't work. All right, start and end vertices are different. Okay, start and end vertices are different. Okay, so basically, and I told you this before, start does not equal end. All right, so they're different. That's what I mean by different. Start point does not equal end point. And the key idea on this one is what's true about vertices in all Euler path cases, this is important, is that there's exactly two odd vertices. Exactly two odd vertices. Okay, very, very important. Two odd vertices only in a path, all even in a circuit. Very important. Once you know that, then your life's a lot easier when you're trying to find an Euler path or an Euler circuit. So now let's formalize everything here. Let's state the existence theorems that Euler came up with back in the day in the 18th century. All right. So if a graph has any odd vertices, okay, if a graph has any odd vertices, then it cannot have an Euler circuit. Cannot. Okay, have an Euler circuit. All right, as I said before, they all have to be even. Let's put a little caveat right there. Okay, they must all be even. Okay, number 2, or letter B, says if a graph is connected and every vertex is even, okay, then, all right, it has at least one, let's highlight that, at least one Euler circuit. It may have more, okay? It may have more than one. Okay, a little caveat there. Okay, number 2, Euler Path theorems. Okay, this is the first one was Euler circuits. The next one here, Euler paths. Okay, now this is what Euclid said back in the day. If a graph has more than two odd vertices, more, all right, and then two odd, whoops, gotta spell that right, more than two odd vertices, keyword is odd, all right, then it cannot have an Euler path. Cannot have an Euler path. Why? Because you have to have exactly 2. So that's part B. If a connected graph, it has to be connected, all right, has exactly 2 odd vertices, all right, then it has at least 1 Euler path. At least 1, all right, Euler path. That's keywords right here, Euler path, starting at one vertex and ending at the other, okay? You start at an odd, end at a different odd. So let's put that in red. Start at an odd, okay? End at a different odd. End at a different odd vertex. Okay, that is for an Euler path. Start in an odd, end at a different odd. Okay, so you got to remember the basic ideas that Euler figured out back in the 1700s. If you want to research exactly why and get into the proof of why, you can read through this and also research on your own. And you can take a look at the rationale behind these theorems. The rationale is the why. Okay, you can do that. We right now are just going to basically apply it. Okay, before we do though, I do want to come up with a couple other theorems that deal with the sum of the degrees and the number of edges. Now, I kind of alluded to the ideas back in the previous example, which I will refer to back when we do this, because I talked about the sum of the degrees and the total number of degrees for each one of these graphs. Like right here for graph 1, there was 8 total degrees and there were 4 edges. And graph 2, there was 10 degrees, 10 total degrees, and 5 edges. And I asked if there was a relationship, like right here, a relationship between the two, and that's what we want to study and formalize right now. So we're going to do the activity once again, just to hit it home and see the relationship. And number 2, more importantly, state it formally, because in mathematics we always formalize things, right? They're called theorems. So what we want to do in these graphs 6, 7, and 8 here, in this figure right here, is we want to figure out the sum, and then secondly, the total number of edges in each graph. Okay, so let's go ahead and do that. So we're going to count the edges first, just for fun here. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 edges right here. Now in red, we're going to do the degrees. So red's going to be the degrees like we always do. So degree 2, 3, 3, 2, 2, and 2. Okay, so we only have 2 odd vertices, C and D. Everything else is a 2. So 2, 2, 2, 2, 2. Okay, so we got 6. All right, 6 and let me see, 6, 12 plus 4 more. Ooh, that's 16. So we have 16 total degrees. Sum of the degrees is the total, 16 total degrees. All right, let's do that for all of them, okay? But let's count the edges first. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 edges. Okay, and let's count the degrees. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, that's 8 right there, 8 degrees. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so A is degree 5, B degree 5, C degree 5, D is degree 3, E degree 8, and F degree 4. So that's 15 and 15, that's 30. That's 30 total degrees right there. All right, and the last graph, what do we have? So we have 1, 2, 3, 4, 5, 6 total degrees, and excuse me, six total edges. And what are the degrees? We have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So they're all 3. Guess what? 3 times 4 is 12. So 12 total degrees. And if you notice right here that the sum of the degrees, right here, the sum of the degrees is always twice as large as the number of edges, all right? It should be obvious. 16 is 2 times as big as 8, okay? Twice as big. And this right here, 30 is twice that of 15. And 12 is obviously 2 times as big as this. So it's twice as big. Okay, twice as big. So the sum of the degrees is always 2 times the total number of edges. Twice meaning 2 times as big, 2 times as big, 2 times as big. That's what I'm talking about. So formally, it looks like this. So let's take a look at the observation right here. The observation is that the first thing is that the sum of the degrees is equal to 2 times or twice the number of edges. So number 1, sum of degrees is equal to twice, all right, twice the number of edges. Okay, or if that's the case, the number of edges is half the sum, right? 8 is half of 16, 15 is half of 30, 6 is half of 12. So number 2, the other way you can put it right here, is that the number of edges is going to be equal to 1/2 the sum of the degrees. All right, 8 is 1/2 of 16, 15 is 1/2 of 30, 6 is 1/2 of 12, and so on. All right, so in other words, when Euler, okay, which is our main man here, when he talks about the sum of the degrees theorem here, he said that the sum, let's put this big bold in red because these are our theorems, right? All right, sum of the degrees of all the vertices equals, okay, equals twice the number of edges. And a graph always, all right, has an even number of odd vertices. That's a little caveat, okay? Always has an even number of odd vertices. It's impossible to have an odd number of odds. Okay, so it's a little sub-theorem called corollary, okay? Now, let's state some other facts here. So in a graph here, in the connected graph here, in a connected graph, if you have 0 odd vertices, and remember, we're talking about odd vertices here. If you don't have any odd vertices, that means that you have all even. Okay, what does that mean? You have a Euler circuit. All right, if you have exactly 2 odd vertices, rest are even. Okay, that tells you you have an Euler path. Okay, and also, if you have an even number of odd vertices, which I stated all the way up here, right here, if you have an even number of odds, like 2 or more than 2 odd vertices, like 4 odds, 6 odds, 8 odds, and so on, okay, no path exists. No Euler path exists. Okay, it's impossible to form an Euler path given more than 2 odd vertices. And then if you have 1, 3, or 5, an odd number of odds, well, up here I said there is always an even number of odds. So down here, this is impossible. Okay? If you think there is, then you counted wrong. Okay? Now, the little note here, let me just point out something here. If there's more than 2 odd vertices and no other path exists, that brings us to remember the bridges of Konigsberg. Okay, so I just wanted to make a little point of this before we move on. Okay, so remember Konigsberg, or recall the 7 bridges of Konigsberg. 7 bridges, oh, just got to spell that right. So bridges of Konigsberg. Okay, I'm going to recreate the graph basically and just talk about it briefly because I didn't at that time when I talked about Knigsberg, I said it was impossible because Euler said it was impossible, but I really didn't discuss why because we didn't have the right tools yet. But now we do. So the Graph of Kongsberg, if you remember, it looks like this. Okay, so there are two islands. They're in the middle here, and you had an upper bank and then you had a lower bank right here. And then in between these land masses were two bridges here, a bridge here, and a bridge here, and a bridge here. Now, if you analyze the degrees, we now know about degrees. We got 1, 2, 3, 3 up here, 1, 2, 3, 4, 5, 5 degrees here, 1, 2, 3 here, and then 1, 2, 3, we got 3 here. Notice that we have 4 odd vertices. Okay, there's 4 odd vertices. And up here I said, if you have 4, 6, or 8, or anything more than 2 odd vertices, all right, there's no Euler path exists. Okay, no Euler path exists. All right, only if you have 2 odds. So this is the magic number here. If you have 2 odd vertices, you can have an Euler path. If you have more than 2 odd vertices, like we have in the real situation back in the 18th century where there were 7 bridges of Konigsberg, today Kaliningrad, well then you know it's not possible. An Euler walk or an Euler path traveling the bridges is not possible because of the fact that we have 4 odd vertices. All right, and that's the reason why. And the locals there in Konigsberg back in the 18th century didn't know that until Euler came around and he proved it. And he used his logic and deduction to prove that. And it was pretty amazing. He was the inventor of graph theory, and then others after him just really made it explode and became a huge subject in mathematics, which has so many different applications. It's incredible. What you guys have to do is get good, right? So we have what's called homework right here, right? We have homework. All right, so guys, do that, do your best, and give it a shot. Check with my answers here, and I will see you in my next lesson. Let's see here. What is my next lesson? Let's see. Let's go. Section 5, 6. Oh, look at this. We're going to be talking about Flory's algorithm here. I'm not going to discuss that now, but hey, remember this is a video, and if you need to review anything, well, you have the opportunity to because it's a video, and use it to your advantage. And if you need to listen to this more than once, go for it, so you can fully understand what's going on, because I may go too fast. But anyways, this is Mr. Ainsworth. Hope you had a good time. Hopefully you learned something, and I'll see you in my next lesson. And we'll talk about Flory in that one, section 5, 6. In modern math, or what is called discrete mathematics and graph theory. I'll talk to you later. Bye-bye.